This is a transformer question that increases in complexity. So let's solve it part by part. In the first part, you are to explain how a transformer works and how it's able to step down the input voltage. So it's important to recognize that transformer works when there is a changing magnetic field. So make sure you talk about it. And this changing magnetic field is caused by alternating input current. This changing magnetic field is linked over to the secondary coil via the soft iron core, and therefore the secondary coil can now experience the change in magnetic flux. By Faraday's law, whenever there's a change in magnetic flux, there will be an induced EMF form, and if the circuit over here in the secondary part is complete, there will be an induced current that flows. Why is it step down? Don't forget about that. Stepping down, this is a step down transformer because the number of turns in the secondary coil is lesser than that of the primary coil. So right now we have to do some calculation, calculate the output voltage across the secondary coil. So we use the standard transformer equation over here. We are given primary coil has this number of turns, 1600. Secondary coil has 80 turns, and the voltage of the primary coil from the question is 240 volts. We can then determine that the secondary coil voltage is 12 volts, showing that it's again a step down transformer. In part B, we connect something across the secondary coil, which is a resistor and a lamp. You are to first calculate the current in the secondary coil of the transformer. And there are actually two ways to do this. The first way is to determine what is the current in the primary coil, and then use the transformer equation that links the current to the number of turns, assuming it's a 100% efficient transformer. Take note, the current to number of turns formula is a bit different from the voltage to number of turns formula. So make sure you don't confuse them. And we get a current of 3.3 amperes. A second way, which is what I prefer, is actually to use the power equation, just one step, because we are given that the transformer is 100% efficient. So the input power, which is VPIP, is equals to output power over here, which is VSIS. So one step we can get the current to be 3.3 amperes in the secondary coil. Now, given the current here, we can then determine the voltage across the resistance of the this resistor, because you know the current from just now. So you know current, you know resistance, you can find voltage very easily using Ohm's law. That's how we can get 8.33 volts across this resistor. And therefore, finally, we are to calculate the power dissipated in the lamp, and we have the total power in the secondary coil to be 40 watts. The input power to the primary coil is 40, and the output coil also has 40 watts because it's a 100% efficient transformer. So total power is 40 watts, and it must be shared between the resistor and the lamp. So the lamp, the power of the lamp is basically out of 40 watts, minus away how much power and energy is given away to the resistor. So 40 minus current times voltage across the resistance, we will get 12.2 watts as the power across the lamp.